Greetings, good afternoon or good morning. My name is Professor Duke Orata. We are continuing with our thermodynamic lectures. Today we want to look at what we call the Reynolds analogy, where we want to relate the rate of heat transferred to the shear stress. Now, we build down equations which we developed on shear stress and heat transfer in turbulent systems. If you remember, we had Q was minus rho Cp to U V prime T prime. And we also had for shear stress was rho into U prime V prime. And remember, we had resolved, for example, velocity into two components. The instantaneous velocity was the same as the mean velocity plus the velocity fluctuations as a result of those eddy actions, which are normally resulting from the velocity gradients within the fluid system. And also, remember, we modeled the temperature change. The temperature change, because remember, when you're talking about transfer of heat, there must be a temperature differential. There must be a temperature differential for thermal transfer. And so we said also that that temperature could be considered to be, can be resolved into two components, the mean temperature and the temperature as a result of those fluctuations. And so we had two important equations. The tau total, we said, was tau, which was resulting from the viscous component, plus tau resulting from the shear stress component. And so this was rho mu du dy plus rho eta y. And this we called the eddy diffusivity. And similarly for Q, we had minus K dt by dy minus rho Cp eta dt dy. This now was eddy diffusivity associated with the heat transfer. Associated with the heat transfer. So I encourage you to go through our earlier lectures where we have discussed these things extensively so that we build things up systematically. Now, we want to work with these two equations and we'll simply rearrange them. On rearrangement, the first equation, we have tau as equal to, if we make du dy the subject, out of the bracket, we pull it out of the bracket, we have rho v plus rho eta. And so du, so as the subject, we simply cross multiply dy by that and divide. So we have tau dy over rho into v plus the diffusivity, eddy diffusivity. And in the same way, for Q, we can make dt dy, pull it out of the bracket, and that will be K minus rho Cp eta. To make our calculations easier, we know that this thermal conductivity is related to thermal diffusivity. F is equals to kappa rho Cp, where that is thermal diffusivity. And this is thermal conductivity. And of course, that is density versus isobaric heat capacity. And so if we plug this quantity here so that we have terms which we can simplify that bracket there with, then we will have, therefore, that Q. Therefore, that Q is equals to minus T dy into, so if you put in place of K alpha rho Cp minus rho Cp eta. And I repeat, this eta is eddy diffusivity in relation to heat transfer. Now, we can make dt the subject. Therefore, dt will be minus q dy, just cross multiply, divided by these quantities there. Divided by rho Cp into alpha minus, this is plus, alpha plus eta. Now, for this fluid, first of all, we assume that the thermodiffusivity is the same as the kinematic viscosity. And so what does that mean? It means that the behavior of alpha plus eta and v plus eta with respect to the y-axis is similar. In the fluid, we assume that alpha, that is the thermal diffusivity, is equal to V. That's thermal diffusivity is equals to V, that is kinematic viscosity. And the behavior of this fluid with respect to the y-axis is the same. And their behavior, the behavior of alpha plus eta and V plus eta with respect to, that is with respect to the y-axis, is the same. This is not just an abstract assumption. This is true when you have flow on plates, on surfaces, plate surfaces, and in the case of turbulent flow in cylindrical tubes. This is true assumption. This is true in the case of flow on plates and turbulent flow in cylindrical tubes. That's true. Now, very important for us to note that. And therefore, to work with these systems, we had this was rho Cp. We had that rho Cp into alpha plus eta. That was minus q dy. We need these quantities here. We need this, and we need to work with this. And to work with these particular two quantities, we need to have boundaries. And in other words, we have to integrate those quantities to get more information. And to integrate those quantities, we must develop boundaries for those integrations. Now, we know that in this fluid flow, we can develop boundaries. We already have done that repeatedly. This is our y-axis, this is our x-axis. This we associate with u in terms of velocity, that we associate with v. And remember, we said for velocity, for thermal boundary layer, and for velocity boundary layer, and here we have free stream, we can get boundaries which we know. Not unknown boundaries, we know them. We know what happens in these systems. When it's on the plate surface, we know, for example, what no slip means in terms of velocity and so forth. So we know that the thickness of this boundary layer, thermal, is sigma t, and the thickness, that is sigma, and we call that distance L. And we know that L is greater than sigma and sigma t. And so we can use the boundary, which we know, we can use the boundary where y is equals to 0 and y is equals to L. It's a boundary. So we can use this boundary and do the integrations here. Now, so on integration, we have integral of du, u to the wall, the free stream, tau dy, rho plus v plus eta, the eddy diffusivity, integrated from 0 to L. And in the second case here, we can integrate this quantity also. We have the integral from Tw to Ts dt is equals to minus Q dy over rho Cp to alpha plus eta, 0 to L. And it's important to mention, because you have said, that's why we talked about similarity in their behavior, their functional behavior with respect to the y-axis. So alpha is the same as V. That is, the thermal diffusivity is the same as kinematic viscosity. Note that alpha is equal to V. That is the kinematic viscosity, and that is thermodiffusivity. They are equal. And similarly, based on those assumptions which are true practically, then it means that Q over T, tau, is the same as QW over tau W. That is very true. And so we can put the value of Q in relation to the shear stress in our system. Now, so what do we have? We have that US minus UW, which is simply US, is integral. So Q here, cross multiply, so we have QW over W tau dy over rho V plus eta L. And of course, in this particular case, Ts minus Tw, or that theta S, is equals to integral of 0 to L minus Q. Where do you have that? Minus Q dy minus Q dy over rho Cp V plus eta. Rho Cp E plus eta. So we have Qw tau dy, and there is somewhere where we are missing our something here. So we have Qw over tau. We have our Q here in place of the tau. No. We didn't want that one there. So we want, that was our tau. This is where we have put our Q. This is our Q. We have said this is QW over tau W, tau dy over rho Cp alpha plus eta. Rho Cp alpha plus eta. Now in good shape. Let's continue. So we have these two quantities here. This is US. We have said that is US. That's this sides. So theta S over US, like theta S over US. Remember, we have said that kinematic viscosity is the same as alpha. So we can have our theta S, remember, is QW. I've just started with theta S now instead of US. It's QW tau dy over rho Cp alpha plus eta 0 to L. And the negative signs are not important, so we are not going to walk around with them. Over tau dy into rho Cp, rho V dash. But remember we said that the kinematic viscosity is the same as alpha. And so what is alpha? Alpha is K over rho Cp. Alpha is K over rho Cp. Remember that alpha here, alpha is equals to, if we say they're the same, then that's the same as K over rho Cp. K over rho Cp. Now, what do we say to that in terms of these two quantities here? So we have Q, so we can factor this out. So we have, if we divide them, so we have theta S, so we have T tau, T dy, rho to V plus eta, integral from 0 to L. So we can factor that out. So we have Q W tau W Cp Q W tau W Cp, the integral of 0 to L tau dy over alpha plus eta, and where we have divided by, that is theta S over S, we have divided that by, so we have tau rho V plus eta, integral from 0 to L. And remember, we have said that alpha, that is thermal diffusivity, is equal to kinematic viscosity. So these two quantities are the same. They are the same. So these two quantities are the same. So if we pull out this, so we'll have the final expression so on simplification, we have QW, remember the W is wall, tau W, that's the heat, shear stress, Cp, and of course we are left with the integral tau dy, alpha plus eta. Remember alpha is the same as kinematic viscosity, so we pull out that, so we will have it here. So we'll have QW over tau W, QW over tau W. We are forgetting our rho here. We are forgetting our rho Cp. So the rho's will cancel out. QW Cp is theta S over US is equals to QW over rho W CP. So this expression here, notice this is the heat. It's to do with heat transfer at the boundary, and this is the shear stress at the solid boundary, and this is the shear stress solid boundary. So it gives us the ratio of the heat transferred at the solid boundary to the shear stress at the solid boundary. And this is what we call Reynolds analogy. What we call the Reynolds analogy. So we will stop at that particular point. We'll pick up with our other lectures.